Still have a few minutes. Everyone should pick up a program.
They're so shiny, you know? As everyone's going to stay. Yeah,
We're busy.
I understand that deeply.
Did I put that?
Oh. There's so much coffee. I'm pretty sure if we all drink this coffee, we will all die. Okay, sweet. So we will get started so we don't get behind. So I will be your host for today in this room. So we've got two talks in this first session. Our first one is Connor, who I've got to have some sort of vague, interesting introduction for everyone. So like Connor's interesting fact was that he has a twin who accidentally also applied to Rose at the same time.
And she's over there.
He's over here, which is crazy. How do you two not talk to each other? That's worrying. But there you go. So hopefully Connor will communicate some science better than he does with his twin. There we go. Take it away, sir.
All right. Hello, everyone, and welcome, esteemed members of the department and other departments, to my talk about optimizing flag selection and phase order in the Glasgow Haskell compiler. My advisors are Dr. Mike Huner and also Dr. Georg Schied. This is just a little bit of an overview of the things we'll be talking about in today's presentation. And I'm just anticipating this question, so I'm just going to get it out of the way right now, is why Haskell, why the Glasgow Haskell compiler? Well, first, while flag selection and phase order have been discussed quite extensively in other compilers, especially GCC, there's been little to no research done in the Haskell compiler. And also, the Haskell compiler, which is fairly unusual for compilers, is written entirely in Haskell, which will actually help us out later when we discuss the phase order problem. So just stay tuned for that. Now, imagine you're writing some code. What are some very, very basic objectives that you want out of any piece of software you write? I'll tell you some of mine. First, I want it to work. Second, I want it to be readable. And third, and finally, I think we all want our code to be relatively efficient. Now, if efficiency is our main goal, we can just write everything in assembly instructions. However, that wouldn't be very readable. And if we just write everything in high-level languages with no regard to how those might be translated onto machine instructions, that probably wouldn't be very efficient either. But we like writing in high-level languages, so we give the job of translating it and making it efficient to the compiler, which will optimize it in a way that will make it more efficient. So let's go through an example of that. Here I have a program aptly named dumb.c. All it does is add two integers together and returns it. Now, if we give this to the compiler and we tell it to perform no optimization whatsoever, here's what the assembly instructions for that looks like. It takes 2 pages, 2 slides just to show all the instructions. And some of these are extremely dumb. For example, right here, we get a value back from our function. We store it in the EAX register, and then we put it immediately into memory. Then in the very next instruction, we take it out of memory, back into the EAX register, and then we return. It's completely redundant. So what do these instructions look like if we tell the optimizer to optimize to its fullest extent? Looks like this. Just a single instruction, basically. We move the value of 10 into the EAX register, and then we return. It's so much simpler. So what did the compiler do? Well, here are 3 optimizations the compiler probably performed on that code. The first one is function inlining, basically taking the source code from a function and just pasting it where the function was called. Second one is constant folding. If we know what these values are in advance and they're not going to change, we can just compute them ahead of time. And third and finally is register allocation, which gets rid of that redundant instruction that I showed you. All right, those 3 optimizations in the Haskell compiler are controlled by these 3 compiler flags. So that's not many. If you want to find an optimal set, we can brute force that. There's only 3. Well, even if we add 2 more, it's still not that many. Oh, but there's much more than that. And in some of these, I have absolutely no idea what they do. Does anyone here know what this weird-looking compiler flag does? Well, the point is you don't have to know, because the developers of compilers have made presets of flags, what they think that most developers for most programs will want. O0 is perform no optimizations. O1 is to perform a few optimizations, and O2 most of the time is to perform most, if not all, of the possible optimizations. So if O2 is all the optimizations, I mean, why don't we just use O2 all the time? It has the maximum optimizing potential. Well, despite their name, not all optimizations actually will optimize and make your code faster. Some will actually slow things down. So for any specific particular program, there exists some sort of ideal set of flags in which it's the best for that program. O1 and O2 might be good in general cases, but there has to exist some sort of ideal set. So the question is, how can we find this? The search space is so large. How can we find this ideal set? Introducing Bayesian optimization for compiler auto-tuning. Now, I covered other algorithms inside my research, but this is the only one we'll focus on in today's speech. Let's go through these steps. So we have some test data. Next, we're going to find which flags were impactful and unimpactful in changing the runtime. We're going to do this using a random forest. So there's actually a machine learning model embedded inside this machine learning model. Then we're going to create new candidates, but we're not going to run these candidates. Instead, we're going to simulate them. We're going to simulate them in our random forest, and then we're going to get their expected improvement. Expected improvement is just how well we think you'll do against our current optimal result. And then only the one that we think has the highest likelihood of succeeding, that's the one that we add to our training set, and that's the one we run the test suite against. And then we just repeat this. So let's go into some of these steps in a little bit more detail. So how do we determine if something's impactful? Well, we're going to use our random forest for that. This math, just to simplify it greatly, basically says, okay, we have a flag. How well is it at determining what the runtime actually will be? And if it's fairly good at that, it's highly impactful. And if it's not that good at that, it's not impactful. So now that we know what is impactful, we need to create new candidates. Now, when we create a candidate, in the very beginning, when we have no idea what might work and what might not work for a particular program, we want to do as much exploration as possible. But then, as we narrow in on a solution, what we think might be the optimal set of flags for a program, we want to make them more similar to the elements in the training set that spawn these new candidates, and basically just be fine tweaking them. We're going to do that using a decay function. This will allow us to determine how many unimpactful optimizations we should add to our currently existing elements in the training set that have impactful optimizations in them. And so over time, the number of unimpactful optimizations that we're adding to any new candidate just decreases as we try to narrow in on a solution. And then after that, we do the expected improvement step, and we add just what we think is the best performing candidate to the training set, and hopefully it actually is as good as our simulations think it will be. Here are some results. These are the VOCA results highlighted in yellow, and we got improvement across the board over our test programs, which is good. In fact, we even got a remarkable improvement in the mail list program. This is the distribution of some of that data. What's important here is that 0 represents the O2 runtime, so that's the maximum preset in the Haskell compiler, and the dashed blue line is O0. Now, what's interesting here, for example, in mail list, is that O0 and O2 have the same runtime, yet there's things that are much better than that. This just goes to show that O2 does have some very bad optimizations in them, so bad that for specific programs, it's just as bad as having no optimization at all. So this is not the only way to change the source code by enabling optimization flags. It also depends on the order these optimizations are applied. So if we can change the order, then we can use VOCA to find the optimal ordering, and then hopefully we can get an improved runtime from that. So what does this kind of look like? Well, first I'm going to introduce a new optimization, common sub-expression elimination. Basically, if you have something that's computed many times in your program, we're just going to compute it a single time and then just reference that value. Here's another program, dum.hs. This is a Haskell program. It just adds the sum of two squares together and then doubles that result. Now, if we apply function inlining before we apply a common sub-expression elimination, we get this code. And if we apply common sub-expression elimination before we apply inlining, we get this code. Now, you don't have to be a genius or a master in Haskell to understand that these two just look different. But here's a compiler fun fact. We cannot determine the order that the compiler performs these optimizations. That is set by the compiler. There's no settings you can tweak. There's no additional flag you can pass in to change how we'll apply those. But imagine we could change that. Well, first, how could we even do that? Introducing the compiler pipeline inside the Glasgow Haskell compiler. Basically, this is just a list full of compiler passes that the compiler will iterate through and apply to the source code. Now, one thing I've done is put them into a structure that makes me able to identify them. And then I pass in a file into the compiler, which will then determine the new ordering. So it will just read in this file, see what the new positions that each optimization should be placed in, and then it'll just shuffle it around, return it, and then iterate through it like normal. And so, is this very, very simple? Well, it's not as simple as I've made it out to be so far. There's a few caveats. So some optimizations are not in the pipeline. You might remember in the very beginning, I had a list of 50+ optimizations. Well, not all of them exist in this pipeline. Some of them are in other parts of the compiler, and if it's able to change the order of those, it certainly wouldn't be as easy as this. Of the ones that are in the pipeline, some of them shouldn't be moved. I call these the O0 optimizations. They're so simplistic and so essential that they're performed regardless of what flags you pass in. Even if you pass in O0, these optimizations are still performed. Because of that, the compiler freaks out if they're not performed in the order that it thinks they're going to be performed in, and it will fail some of the compiler tests. And third and finally, of the optimizations that we can move around with relative ease, sometimes you just run into some wacky, buggy combination ordering that just causes things to not work anymore. So now that we know we can change the order, we can just use VOCA to optimize. I mean, we already have the algorithm written, you saw it. Unfortunately, we need to discuss one further thing, one change we must make to our VOCA algorithm. When we're dealing with flag selection, those were combinations of flags. But now, since we're dealing with ordering, we have to deal with permutations. So how can we represent that when we're creating new candidates? We can represent it as a graph, just permutation equals graph. So if we have optimization A, B, C, D, E, this would denote that A has to come before B, B before C, and so on and so forth. My research deals with a very essential assumption that for a new ordering, B coming before C might denote most of the change in the runtime. So how do we actually give that information to the compiler and to our BOCA algorithm? Because it might be more important that B comes before C regardless of how far apart they are than something like A coming before C. But we can do that simply by adding more edges in our graph. Now we know that B has to come before C as well. And if we do this to one vertex, of course, we have to do it to all the vertices. So this is what a valid permutation looks like when represented as a graph. And this is how we're going to create new candidates and make sure that everything falls in line. So let's go on to the next step of our algorithm, choosing those impactful and unimpactful optimizations. So perhaps these are our impactful rules, that B has to come before E, that E has to come before C, and A has to come before C. All right, this looks good. So now we're going to add a random unimpactful rule, just like we did for the flag selection problem. Maybe I add this one. Okay, so now this says that B has to come before E, E has to come before B. I thought B had to come before E. This is a contradiction. There's a cycle in our graph. This cannot be a valid permutation anymore. So just randomly adding unimpactful rules just won't work because we might add a contradictory rule. So if we represent our permutations as a graph and we can't have any cycles, so it's a directed graph with no cycles. I wonder if there's a name for that. Yes, a directed acyclic graph. All of our permutations have to be directed acyclic graphs. That's what all this means. And we can leverage some facts about DAGs to create new candidates. So we know that if there's a DAG and we take a subgraph of it, it is also a DAG. We know that all of our permutations are already DAGs. You saw them. And so if we just take the impactful optimizations from those have to be DAGs. If we add rules that existed in that candidate as it existed in our training set and add those to the impactful ones, those are also our DAGs. And then to get the remaining rules to fill in the blanks, we can use a topological sort. This will allow us to create a new permutation. So for the example I showed you earlier, one possible topological sort of this would be DABEC. And so that would be our new permutation. That would be the new order that we would test. You know, I've made a lot of changes to the BOCA algorithm. Should we even call it BOCA anymore? Well, just for distinguishing the two, I'll call it BOCPA, Bayesian Optimization for Compiler Phase Order Auto-Tuning, name pending. So does the algorithm still work? Well, to test this, I added some arbitrary optimizations into the compiler. They don't do anything. However, if I notice that a program has them, if it's the good optimization, I'll just arbitrarily decrease the runtime by 1%. And if it's the bad optimization, I'll just arbitrarily increase the runtime by 1%. Even with such a small change as that, over time, BOCA was able to very effectively discriminate between the two. And by just past 300 iterations, practically every single new candidate had the good optimization in it, and every single bad candidate, and every single candidate was neglecting to include the bad optimization in it. So here are some results for that. Again, we've seen improvement across the board, across all of our test programs. And also, a lot of these improvements are better than even the flag selection problem, which surprised me greatly considering this is kind of supposed to, the order is supposed to be kind of set in stone. You're not supposed to change it. Yet by changing it, we're able to get tons of improvement. Besides that 15% improvement we saw in that mail list. I still understand where that came from, but we got great improvement. And again, we have the distribution here. 0 is the default ordering, the default O2 ordering. And compared to that, again, we have improvement everywhere. Now, one thing you'll notice is not on this distribution is the O0 line, because if you don't include any optimizations, you can put them in whatever order you want. So it just wouldn't make sense for the phase order problem. All right, that is the end of my presentation. Are there any questions?
Let's thank Connor first.
Oh, Jackson.
In just the previous slide, those result graphs, could you talk about exactly what these graphs are showing again?
Sure. So when I run, and actually I'm going to go back to a further one because I think it's more clear there. Yeah. So I run these algorithms many times. And so like, for example, if Boca goes through 10,000 iterations, let's say, it will have 10,000 elements more or less inside of its training set. And the same with all these other algorithms as well. And so they all have different run times. They're distributed, some are better than O2, some are worse. And so this box plot just plots a distribution. So all the ones that are worse than O2 all appear up here. The ones that are better go below 0. And then the dots represent outliers. All right. Any other questions?
Actually, I want to look at one of those plots again.
Sure.
The result of the box in this case.
Right.
So the points here are different, like runs of the algorithm, or is it different combinations or orderings of the sets or both?
These are different. So this is the flag selection graph. So these are different combinations of flags.
So is there across like the different programs you tested here, were there any flags that are like consistently using this flag makes the code worse and consistently making it better? Are there any patterns, or is it super specific to the actual code that we're talking about?
Well, one thing I looked at was for like genetic algorithm in Boca, these are both supposed to converge on a solution. So I was kind of wondering if they'd converge on the same solution. Looking at the research, they never converged. The closest they got was one time genetic algorithm was a subset of what Boca had decided upon. They never converged. However, when I did look at I did an MCA analysis, and some of the optimizations did account for a large amount of the variance. However, when I investigated Boca, even those ones that accounted for most of the variance weren't always chosen to be impactful optimizations.
So that's between your algorithms. What about between the different training programs, like mail list versus sorted? Or were there flags that were good in one and bad in the other? And did it make sense at all?
So are you asking like if they shared some flags?
Yeah. Share the flags themselves and the order of the flags.
Well, for the flag selection problem, it was basically they all had their own sets of flags. There wasn't any, at least any obvious and apparent like sharing of flags. Nothing that was super impactful. In fact, mail list is the one that I always kind of get wacky results because I think it has a very specific set of flags that it must like. And I kind of think that when it comes to the permutation for something like mail list, that mail list's performance, I think, is almost entirely dependent on whether or not some very specific rules are in effect. I think actually for mail list, if there's optimizations that block other optimizations from occurring, I think the rules that block some certain optimizations from occurring are the ones that result in the most improvement for mail list.
This might be a bit of like a meta question, but if you were to like implement all of this research into like into an actual compiler for a piece of code, would this algorithm that you're using, would it be more efficient than like what compilers do normally, like the runtime of like actually finding the most optimal set of flags to use? Or
so there's two issues baked into that. Whether or not this greatly increases the compile time, then how efficient these algorithms are. Like, I mean, if you were going to program something tomorrow and you wanted to make it a little bit faster, would it be reasonable to run these algorithms? The first one about compiler times, it does not greatly increase the compile time, having to import that file, shuffle everything around. However, for the time to run these algorithms, maybe you should only run them right before you're going to make your final binary for release. Because for the flag selection problem, it's not that bad. It still takes a few hours to run for all 4 programs, especially with a lot of iterations. But for the phase order problem, those graph operations, and also some other stuff I do to try to eliminate problem orderings, as I mentioned, some orderings just are buggy, that just creates a lot more runtime, and it significantly slows down the algorithms compared to the flag selection versions. And therefore, only do this when you don't think you're going to make very many more changes to your code, so you don't have to keep running it. That's what I would suggest.
Excellent. That. Any last question? Okay, let's start counter one more time. You were like, we're 24 minutes now, so you probably have 18 minutes. Yeah, it's perfect. We'll wait till 10:30 to start yours, just in case people are coming and going. Nice corners
woke up
and then left or right, if you want.
Oh, nice.
Okay, thank you.
So I threw on this and got the door, so I come up my brain extension for it. So I had to do a lot of heavy lifting to understand what you're talking about. It was good. It seems like a lot of benefits. A lot of benefits. But yeah, it was very well presented. I'm sure you still have to see So yeah, good job.
For the like buggy orders or whatever, could you modify your algorithm to just exclude those from the search space, just like that helps you things out, or is it like buggy only in certain cases?
Yeah, the problem is it's difficult to predict, which orderings are going to be buggy. I've looked through all of the optimizations themselves to see if there's like a comment anywhere that says this optimization must be performed this one, otherwise things will break. But unfortunately, it doesn't say that, so it's difficult to predict them. And so what I've been doing is there's another machine learning model embedded already in this machine learning model, besides the random forest, where every single result that I do get, I record whether or not the compiler test passed, store that in another CSV, and then we use that as training data to see if we think this new one will also work or break. Right. And it's been very accurate. The metrics I've determined have like its precision, accuracy, and recall all above 90%. So pretty good.
And the training set of those are like 90% of the training set works, so only 10% break.
It is skewed in one direction, skewed towards working, but I'd say probably 60% of them work, 40% of them fail. Except I also tried saying if I could find any orderings of the O0 optimizations, which I mentioned, every single one of them failed. I probably tried 2,500 of them. Fail. I'm not sure there exists a possibility.
Are you gonna go to India's? Or are you allowed to
We're supposed to be relevant, not in this room, just doing presentations. I'm going to go to India to conduct this meeting, but that ends early on Monday.
Okay, I think we should be noticing your design stuff by that time. So policy land is in, and it is.
What time is it?
2:10.
I'm definitely this time.
Okay.
I'm hoping.
You did a good job though. I'm gonna go find something to eat and wake up hopefully. So
Good open for snacks in the CS lab.
Oh, there are. I will
Stephen's talk.
Yeah, after this presentation.
But, you know.
Wait, what?
The snacks after this presentation.
Can I,
The snacks aren't there yet, man.
oh, they're not? I'm just gonna go to the bounds.
Try flying with.
Why are you doing that? Oh, yeah, that's right. You should probably do that. Yeah. Did you just ask what the recording, the fact that it was on the program and well, but the same issue with the code. Yeah. Did that happen effectively? Yeah. Hopefully we change the optimizations and don't trigger some global flags somewhere, don't break things, but that's very fun. Did you use it instead?
Yours are that one, right?
Yes,
Yeah.
yes. Yeah, that's.
Yeah.
Just like, I guess. Come on. I mean, it's probably.
Sure.
That's
Is
like, well, isn't that what I like?
Muhammad in Poland?
Steam is in the first place, Pascal and Symposium.
Yeah.
Python doesn't. Well, it can't.
How many of you have had class in here? At all? Have you ever been in this room?
I got cybersecurity somewhere on here.
Right. Seminar. Interesting. I end up teaching in this room all the time, and yet it seems like nobody has class in this room, so that confuses me.
No, I just look at these. Finish writing and some decent.
Okay. So I think that is about 10:30. So we'll get this party started so we can get to the snacks and see what we got. Stephen is going to be presenting here. So Stephen, interesting fact is he grew up between Korea, Taiwan, and India, I think, right? Which is crazy. So I'm sure Terre Haute has been the most exciting place he's lived for the last 4 years, for sure. And so he'll tell us a little bit more about his research. Take it away, sir.
Thank you. Thank you everyone for coming here. My name is Stephen Jung. I've been working on my thesis with Dr. Marquez. And today I want to talk about mutation coverage. And I'll be explaining mutation coverage by comparing two different kinds of tests. First, tests that were manually written by developers versus tests that were automatically generated using the latest software testing tool. And by the end of this presentation, everyone here will understand what mutation coverage is and understand the significance of mutation coverage in the software testing field. But before I talk about mutation coverage, I want to talk about code coverage, which is the more widely adopted metric to assess the quality of your test cases. By definition, code coverage is a metric that can help you understand how much of your code is tested. And there are many different ways to calculate the code coverage. You can calculate by the number of lines being executed, which is known as line coverage, or you can calculate by the number of branches being executed, which is called branch coverage. And the image on the right represents a very typical code coverage report. The first column represents like salt modules or individual programs in the entire code base. The important columns are the last two columns, the line coverage and the branch coverage, represented as bar graphs. And you can see that there's a lot more red than green, which indicates that this particular code base has really low line coverage and really low branch coverage. So typically what software engineers do is they will look at code report like this and manually generate test cases to increase the line coverage as well as the branch coverage. But such task is very boring and tedious. So there are software testing tools that can automate the process of generating the test cases. And one of the tools I want to talk about today is called CLE, which is powered by Symbolic Execution Engine. It's an automatic test data generation tool, which symbolically executes the program to explore all the possible paths. And by doing so, it can generate specific test data for maximal code coverage. To give an overview of how CLE works, you first start out with the C code, and it can be any programming languages as long as the LLVM compiler supports. The LLVM compiler compiles the C code to LLVM bitcode, which is simply an intermediate representation of the code. And this LLVM bitcode gets fed into the CLE symbolic execution engine, where it does some fancy mathematics like constraint solver to generate specific test data for each of the explored paths. And to delve deeper into how the CLE symbolic execution works, suppose there is a simple program that declares variables x, y, and z. And there's an if statement as well as the else statement. If you look at the very first rectangular block, symbolic execution represented the variables x and y as some kind of symbolic variables, capital letter X and Y. And the next rectangular block represents the very first if statement, x is less than y. And a constraint solver will basically look at these constraints and solve specific test data for both of the true statement and another for the false statement. Okay, so now that we know how CLE works, I want to explain about how the performance of CLE. So when CLE symbolic execution engine was executed on GNU Core Utils program, and for those of you who don't know what GNU Core Utils is, it's a standard set of programs that exist in Unix operating system that interacts with low-level operating system API. So CLE was able to find 10 unique bugs, and these were usually memory error crashes. And they were able to significantly increase the code coverage. So if you look at the table, the line coverage for GNU test was 68.4%, whereas for CLE, the line coverage was 90.9%, a significant code coverage, line coverage improvement. But knowing that CLE can generate really high line coverage and really high branch coverage, the question I had was, is CLE generating higher quality tests? And I wanted to find that out by determining the mutation coverage. So apart from my core question of determining the mutation coverage between the two tests, I had 4 other research questions that I would like to address. Number 1, how do software complexity and initial coverage influence mutation coverage in manual versus CLE-generated test for GNU Core Utils? Number 2, which mutation operators are most effective at killing mutants? Number 3, under what conditions do CLE-generated tests achieve better mutation coverage than manual tests for GNU Core Utils? And lastly, how can automated tests generated by CLE improve mutation coverage in existing manual tests? And I'll address these individual research questions in my next slides. Okay, to shift gears a bit, how do you actually calculate the mutation coverage? Well, you first start out with the source code. In my case, the source code is one of the GNU Core Utils program. And the source code will undergo some kind of minor modification based on my defined mutation operator. And there are many different kinds of mutation operator. For example, a conditional logic mutation operator. So a source code, for example, will undergo some kind of minor modification that changes the conditional logic, say not equals to equals equals, or greater than equal to less than or equal. And these minor modifications are known as mutants. Now, my existing test, in this case, the GNU test, as well as the CLE test, will execute against these modified program. And if the test case passes, then the mutant is said to be survived. And if the test case fails, then the mutant is said to be killed. And to calculate the mutation coverage, it's simply the number of killed mutants over the total number of mutants. Okay, here is a practical example of how mutation testing is done. This is how typically software engineers would look at the survived mutants to improve their test cases. To give a little bit more context on what we're actually trying to improve here, suppose there is a calculator app that has this function called add, which takes in two parameters, A and B, and simply adds A plus B. Now the mutant I created, I simply modified A plus B to A plus A. And if you look at the weak test, it has one assert statement to check to see if 2 plus 2 equals 4. Now, if you execute this weak test against the mutant, the test case passes, meaning the mutant survives. Now, engineers will look at this and try to improve the test by trying killing the mutant. So if you look at the strong test, it has another assert statement where it checks to see if 3 plus 2 equals 5. And when you execute the strong test against the mutant, this time the test case fails, meaning the mutant gets killed. Notice how the line coverage for both the weak test and the strong test is 100%, but the mutation score is different. So it really tells you that line coverage can be a misleading metric when evaluating the quality of the test case, and that mutation coverage is a better metric to assess the quality of the test. Okay, now I want to talk about my experiment methods to how I assessed the mutation coverage for both the CLE and GNU test. First, I generated 20 mutations per program across 7 GNU core utilities for sequence, cat, printf, sort, date, chcon, and chgroup. So I basically created 140 total mutations using GPT. And the mutants I created fall into one of these 5 categories. Either the conditional logic, the unary bitwise, the pointer direction, block removal, or the function argument modifications. And then after generating these mutations, I executed both the GNU manual test as well as the CLE automatic test against the mutants. To explain more about how I actually generated the mutants, because there are definitely many different ways to generate the mutations. I first utilized CLE to generate the test data for each GNU core utilities program. And then I generated the line coverage report using GCov. And then I supplied the coverage report as well as the source code to GPT for in order to mutate only the covered lines. And then finally, I conducted manual validation for the mutants to see if they compiled or not. So the image on the right represents one of the mutations for the date program. And you can see that it modified equals equals to not equals. Now, these two data, the image on the left represents the source code of one of the GNU core utils, and the image on the right represents the GCov report from CLE. And I basically fed in these two data into GPT to generate the mutations. And again, I fed in the GCov report to only mutate the covered lines. Now, technically, I should have generated both the GCov report for CLE as well as GNU, and somehow combined the GCov report to cover the combined or common covered lines. But due to time constraint, I only fed in the GCov report for CLE. And surprisingly, if you feed in these two information into GPT, it will generate valid mutations. Here's a sample data of what it looks like after running all my experiments. This is for the sequence GNU core utils program. Each of the individual rows represent mutations, and the mutant information contains specific line number of where it was mutated at, the mutant description. So if you look at the first mutant, it modified equals equals to not equals, and which is a type of a conditional logic mutant. The important columns are the last two columns, the GNU test and the CLE test. Number 1 represents that the mutant is killed, and 0 represents the mutant is survived. So the mutation score for the GNU test would be 100% because all the 5 mutants were killed, whereas the mutation score for the CLE test is only 20% because only 1 mutant was killed out of the total 5. Okay, so GNU versus CLE test comparative study results. Here are my experiment results. It turned out that GNU test achieved higher mutation coverage compared to CLE, despite CLE's higher code coverage, and that there were notable exceptions where CLE performed better than GNU test, specifically in specific rare cases. And finally, code coverage and mutation coverage revealed distinct insights. And I'll cover these statements in the next slides. First, to talk about my statistical comparison between GNU versus CLE test, just like any other statistical test, you have to first set your hypothesis. My null hypothesis states that there is no significant difference in mutation coverage between GNU and CLE test. And my alternative hypothesis states that there is a clear significant difference in mutation coverage between the two. I also perform the McNemer's test, which is a standard method to compare between 2 controlled categorical groups. And the p-value threshold that I set was 0.05, which is a typical p-value threshold to determine your statistical significance. Any value less than 0.05 means that I can safely reject my null hypothesis. So the rows colored in green are the programs that I can safely reject my null hypothesis, which means that there is a clear difference in mutation coverage between the GNU and CLE test. And for all of those programs, sequence, printf, sort, and cat, the mutation score for the GNU test was significantly higher than the CLE test. There was one exception, however, which was the date program, where the mutation score was higher for CLE. I also studied which mutation operators were effective at killing the mutants. There were total 5 mutation operators that I had: conditional logic, unary and bitwise, pointer direction, block removal, and function argument modifications. And pretty much all the mutation operators, except for one, performed better for the GNU test. The unary and bitwise mutation operator performed better for CLE. Now, this is interesting because I assumed, maybe the conditional logic mutation operator would have the equivalent mutation coverage between the two because of the nature of symbolic execution, only looking at the conditional logic. Here's another interesting observation where CLE performed better than GNU test. If you look at this specific mutant, this is from the date program where it modified set time not equal 0 to set time equals 0. And for the CLE test, this mutant was killed, indicating that it is effective at detecting the faults. For the GNU test, this specific mutant survived, revealing that there's weakness in handling the specific conditional logic. And the implication suggests that there is a potential gap in handling this conditional logic error. And there were total 30 cases like this where the mutant was killed for CLE but survived for GNU test out of the total 120 mutations. Okay, conclusion and implication. So recall my research title, Human-Generated Test versus Automatically Generated Test. Well, it turns out that human-generated tests have much higher mutation coverage than the automatically generated test. And this is likely because the domain knowledge is embedded in the test case and because there are specific assertions in the test case, whereas the automatic generated tests do not. But this doesn't mean that test case generator like CLE are insignificant. There are certain rare cases where CLE performed better than GNU, indicating that you could use the test data from CLE to augment existing test cases to improve the mutation coverage. That's it. Thank you for listening.
Thanks, Steve.
Yes.
So it seems like, could you get a mutation that, it changed the code, but the mutation was actually in a version that still allowed the, like, the code to be successful? Like it was not error prone, that's fine.
All the mutants were validated to see if they compiled. Like they would be successfully compiled.
Well, I mean, like, yeah, that's what I mean.
Different mutants to be, yes. So I think those are called equivalent mutants. And those mutants indicate that they show same behavior as the original code. And normally you would calculate, like you would get rid of those mutants from your mutation coverage calculation.
How would you, my second question on my follow-up is, how can you determine that those mutants are are equivalent? Because if you just run the test again, well, that's the whole reason why we're doing this, right?
Yes. You would have to like manually check whether or not the behavior is same. There's no like automatic way of doing this. Yes.
So for the, you mentioned, I think there were 3 where CLE found tested in one student. For those, I realize it's a small sample, but are there like patterns they share where it's like both a pointer thing and a logic thing, where it's like you could maybe make a style guide, like when writing tests, if you have a line of code that has a conditional and a pointer, double check it, here's how you make tests that work. Or are they just all 3 totally random different things?
So the 3 mutants where the mutant was killed for CLE but survived for GNU test, 2 were conditional logic mutants, and 1 was unary and bitwise. And I think 2 of those were from the date program, which was the outlier where CLE performed better than GNU.
So like with that, is there, since kind of your outcome here is like we have to manually write the tests essentially, what advice would you have for an engineer writing tests to make sure they don't miss cases like this?
Okay. Absolutely use mutation coverage over line coverage. I think that would be the first thing. And just use all the software testing tools out there to see if your test cases are robust at detecting faults.
I got one more too. Could you go to the stat slide? I just want to make sure I understand the point of this, because you're trying to show like if they find different tests, right? Or if the tests are stronger under the GNU versus the CLE, right? It seems to me though, like even if GNU has one stronger test, the answer is yes, GNU is better, or vice versa. So what's the point of doing the stats if I just want to make sure I always have the best tests? For me, it doesn't, I don't understand the point of doing this.
Okay, so the objective here was to see if there is actually a clear difference in mutation coverage between the 2. I assumed, maybe the CLE test would have, equivalent mutation coverage. But turns out, the GNU test just had significantly higher mutation coverage than the CLE test.
Okay, so this is just about the coverage in general.
Yes.
So if they have the exact same coverage, but for totally different sets of mutation,
Yes.
your null hypothesis would not be invalidated here. Okay, I see. So this isn't telling us that there's one extra good test. This is just telling us, are there more of the code coverage by mutation?
So this is a pairwise analysis?
Pairwise.
Yeah, it's pairwise, so to actually see if they're actually different. Like,
Okay.
it's not just how many. Yeah,
Okay.
yeah.
So then in that case, it still feels a little like if there's one extra test, don't care how many tests we did.
Yeah.
Seems like better is the answer. But that may not be statistically significant.
Right. Yes.
Right.
Yeah.
Okay.
Yeah.
Excellent. Let's thank Stephen one last time. We should have some snacks set up in the PS lab at 225. Go crazy.
I didn't know.
Be back later. Bye, Buffalo.
Bye.